I'm Doug, Stand-Up Physicist. Today I'd like to discuss Albert Einstein. I'm sure anybody watching a show as nerdly as this one knows a few things about Albert Einstein. So I hope to add to your collection of Einstein stories. One of the less well-known facts about Einstein was that he played the violin. Now, there are many people, myself included, who are good at math and physics and play musical instruments. Why is that? Well, here's my own theory. Information in the brain is stored not only in a location, but in a rhythm of brain circuits. By playing a musical instrument, you make your brain think more precisely in time. And that precision in thinking helps to figure out math and physics, which definitely requires a lot of precise thinking. But even more than that, Einstein improvised on the violin. I was surprised to hear this, because I knew you could improvise on the piano, and on a saxophone, and on a bass, and anything in a jazz band, but the violin? Well, improvisation is about the mind. What you do in an improvisation is you must embrace everything that's happening at the moment. And based on that, you must take the next step forward. Now, sometimes that step sounds a little off, but it's not. It's just unexpected. And to be good at improvisation is to embrace the unexpected and to incorporate it and make it work with everything else that's going on. And clearly, that's the kind of mind that Einstein had. He was good at improvising on the violin, and he was even better at improvising in physics, getting results that looked completely unexpected, embracing them, and building something beautiful out of it. If you want the best review of Einstein's work, I recommend Subtle is the Lord, The Science and Life of Albert Einstein by Abraham Pays. The title is based on a quote of his. Subtle is the Lord, but he is not malicious. That's supposed to indicate that nature is open and honest with us. It's just incredibly difficult to understand what she's saying. Einstein's amazing skill was subtle improvisation. I got to read to you a couple of lines from here that I thought were very good. Were I asked for a one-sentence biography of Albert Einstein, I would say he was the freest man I have ever known. Had I to compose a one-sentence scientific biography of him, I would write, better than anyone before or after him, he knew how to invent invariance principles and make use of statistical fluctuations. Were I permitted to use one illustration, I would offer the following drawing. We have special relativity, the physics of going very fast, leads to general relativity, which is the physics of going in any old direction you feel like. And on the other side you have statistical physics, thermodynamics, what random particles do with each other, leads to quantum mechanics. And his vision was that those two would come together in a unified field theory to explain how gravity and light work together and why quantum mechanics had to be the way it was. Now, I made those arrows leading to unified field theory as dashes because it was clear he did not succeed in finding his unified field theory. My own efforts to solve this riddle is very different. Same goal, but different approach. For me, the core is that equation in the red box, a four-dimensional wave equation. Physicists know that equation is all you need to explain how light works. Officially, it is called the Maxwell equations in the Lorentz gauge. What Einstein did to develop special relativity was look at the Maxwell equations, see a logical consequence of that. That's the speed of light was fixed. That was a subtle observation, which he then looked at all the consequences, improvised off of that observation, and developed all the consequences of special relativity. The top part of this diagram is absolutely standard. What I am trying to do is to see how gravity could also live inside that four-dimensional wave equation. That is subtle, I argue, because that J could either be positive for like electrical charges repelling, or it could be negative for like mass charges attracting. I get to classical physics by taking a certain type of derivative. It is the classical derivative. There's nothing odd about causality. This leads to that other thing. But if you are forced to take a different type of derivative, where you absolutely must take the norm of the derivative, which means you must look at everything that could contribute to the change, then you start doing quantum mechanics. So that, in a diagram, is how I hope to unify gravity and light and explain the difference between classical and quantum mechanics. My father met Albert Einstein. My grandfather worked at Princeton University, where Albert Einstein also worked, but not as a physicist. My grandfather was an international diplomat. He was critical in setting up the League of Nations. So my grandfather and father were walking across the campus one day where they met Albert, who was also walking around the campus contemplating the subtleties of the universe. And he looked my father straight in the eye and shook his hand, and then they went off their separate ways. What surprised my father was that decades later, he still remembered the experience. And I've wondered, why would that be so? Albert Einstein was no magician. And I think it was because he was in the moment, with my father, accepting my father as he happened to be, and making a connection. And that's what I try and do in my own personal interactions. Now I need to explain the background here. I'd like to introduce you to my two oil paintings, Gray Albert and Turquoise Einstein. They happened because of an art class I was taking on Photoshop, which is a computer program to manipulate digital images. We were given the assignment of colorizing a black and white photograph. I had a calendar with lots of pictures of Einstein lost in thought, considering the subtleties of the universe. And one of those photographs showed Einstein as happy. And so I gravitated to that one and chose to work on it. because Einstein actually was a jovial fellow. He found a lot to be funny about in the world. So I went to the library and looked up the expert at colorizing, Andy Warhol. I looked through his body of work, and the one that I enjoyed the most was his image, Turquoise Maryland. So I took little notes, went back to the computer, and created Turquoise Einstein. I was pleased with the 8.5 by 11, but I wanted it bigger. So I found out that for about $300, I could get a computer image blown up to that size. But I knew that it would look better if it was actually an oil painting. So I started to study how people do oil paintings. I found out that for about $300, I could end up with a professional set of oil paints, brushes, easels. And I read up on the different processes that are used and decided to use Norman Rockwell's technique. What he did was he projected a slide onto a canvas and then painted from there. It still takes some skill, but it helps a lot in getting the paint where it should be. But I used another technique. I projected the slide upside down on the canvas. The reason is that the brain has all these symbols for how to draw an eye, or a nose, or a mouth. And to get away from that symbol system and to use the brain's ability to actually see what's there, which are these unusual shapes and subtle changes in tone. By projecting upside down, you can actually see that much better and therefore paint better. Gray Albert here is supposed to show how Einstein is so conservative and well integrated into standard physics. His most famous equation is E equals gamma mc squared. Now it's usually written without the gamma because that's Greek and that means it's Greek to most people. I actually think the equation is all about the gamma. Physicists say, at least for a general audience, it's okay to drop the gamma because it's so close to 1, but it's not exactly 1. And I think that's the thing to understand. When they teach special relativity, they usually talk about either those things that are conserved or are invariance principles, and those things that are relative. But what should be done is that you always get both. They should always talk about what's invariant and what is relative. I'll give you 2 examples of this. There was an experiment to measure the speed of light, done in the 1800s. Light was moving off a mirror, bouncing off a mirror, back and forth like that. And they had it going another direction. And they said, well, will we end up with measuring the same speed? Well, the thing is that this thing was turning with the Earth, which goes at actually quite a good rotational speed. So you would think that the speed going like this would probably add to the speed of light, and therefore the speed of light this way should be greater than this. That's a reasonable thing. But it's not the way nature works. Nature is more subtle than that. They did the experiment, same exact thing, no matter which direction it was measured. But something does change. What changes when you measure these speeds is that the frequency this way is higher and the wavelength is lower. And the result of those 2 effects is that the speed of light is invariant. It's constant. Another example they do is they talk about your clock and your meter stick when you're in a rocket ship. Nothing changes about them. And if somebody else is in a rocket ship going the other direction really fast, and they have a clock, and they have a meter stick, nothing is wrong with their meter stick or clock. But if you look up at their clock and meter stick, you'll say, their clock looks like it's going slow, and their meter stick looks a little short to me. And they look down at you and they say, excuse me, your clock is slow, your meter stick is short. Well, both are true. Both are relative measurements. But what they don't tell you is the invariance principle. Now, hopefully you remember Pythagoras' theorem about right triangles, where one side, a squared, plus another side, b squared, equals the diagonal, c squared. Einstein worked with this, but with a subtle variation. He did it in 4 dimensions, and he said x squared plus y squared plus z squared minus t squared. That's going to be an invariance. Now that minus t, it does all kinds of unusual, unexpected things. But that's okay. He took that and basically built most of special relativity around that invariance principle. Turquoise Einstein is supposed to represent Einstein's most radical notion, his way of explaining how gravity works. The reason it's so radical is that it doesn't get along with the rest of physics. Quantum mechanics is what's called a linear theory. But general relativity is nonlinear. And despite 80 years of effort by the brightest minds on the planet, it still doesn't get along. But it does agree with the data. So we do have to accept it as having truth. The question is, why is it out there by itself? What do we need to do to bring gravity in with the rest of physics? My own effort is summarized on this t-shirt, where we pay respect to Albert, and we have my equation of J equals box squared A. Now that looks simple, subtle, so much like how electromagnetism works. But if you realize that J could be plus or minus and have either positive similar charges attracting or repelling, we might be able to achieve the unification that Einstein worked so hard at. Thank you very much.
All the girls in the classroom think he's hot. He shows up wearing the sandals with the white socks. He hears them giggling while he's got his back to the class. He thinks he's got an eraser mark on his ass. And all the girls from the hall show up to hear him talk, even though most of the time he's covered in chalk. Math prof, rock star. Math prof, rock star. Oh yeah. Math prof, rock star. He was young, he never thought that he would be a math prof, rock star. And after hours outside of his office, there's a line waiting, full of girls who want to ask about their quadratic equations. She leans over the desk and twirls a pencil in her hair, complains the grade he gave her was way unfair. And all the professors, they laugh about it and they wish him well. The guys in the class are all just jealous as hell. Math prof, rock star.
Let's think about the most important physicists of all times. There would be Sir Isaac Newton, Albert Einstein, and Pokey Reese. No, I'm sorry, he's a Red Sox. Okay, these guys were born in very different times. And they had different religions and different worldviews. But what did they share in common? Well, if you spent a lot of time in the basement of libraries reading up on these guys and sniffing an awful lot of glue, you would come to realize that they both had the ability to put their foot behind their head. So let's see how well I can do that. Well, here's my foot. There's my head. I think I'm going to have to take my hat off here. I wonder if Hawking can do this. Uh-oh. Uh-oh. Please help me. My leg fell off and it's bleeding. Please help me.
Oh yeah.